Welcome to another class in Construction Management 324, Construction Planning and Scheduling, and today we're going to start discussing another scheduling technique, which is activity on node, also known as precedence diagramming method. So either known as AON, activity on node, or precedence diagramming method, PDM. Last time we discussed ADM, activity on arrow, or AOA, activity on arrow, or ADM, arrow diagramming method. And we learned about the network flow from left to right, and we learned about the nodes that represent the start event and the finish event of the activity, and the line connecting these two nodes representing the activity itself. And we learned about some of the difficulties representing activities that start at the same time, finish at the same time, and having a common predecessor or a common successor. And we had to resort to using the dummy activities in this case. And another problem with ADM is that it only allowed for one type of relationship linking the activities, which is commonly known as finish to start, where the successor has to start only after the predecessor was complete. While this is not always the logic connecting the activities in the construction industry, we had to look for another alternative, especially also with the dummy activities not being the most intuitive thing to understand. We needed to look at a better way of representing activities, and that basically was the reason why activity on node or precedence diagramming method started. So we're going to discuss what's the activity on node network. We're going to discuss the network calculations for AON or PDM networks. We're going to look at the precedence diagrams, and we're going to look at the precedence diagram calculations, which are going to be pretty much the same as the ones in arrow diagramming method. So this PDM or precedence diagramming method, also known as activity on node network, instead of the activity being represented by two nodes with an arrow connecting them, so all of these three entities represented the activity, we're going to consolidate all the information about the activity into one box, and that box is going to be the activity itself rather than the line. The lines in this case that you can see on the screen represent the relationship between the activities. So it uses the node or box to represent the activity, as opposed to the arrow used with the activity on arrow or AOA network. The arrows represent logical relationships, and their length does not reflect any special meaning. So again, this is not drawn to scale. The length of all the arrows are pretty much the same, so it does not represent any special significance. And the good advantage that we have in a precedence diagramming method is that we do not have any dummy activities. So when you look, for example, at a Gantt chart or a bar chart that has 5 bars representing 5 activities, the translation is going to be 1 to 1. Each bar is going to be translated into one activity. We could not do that in arrow diagramming method, because in case you had some activities overlapping or you had some lag between the activities, you had to introduce another activity to represent that lag, or you had to break the activity into more than 2 sections to represent the overlap. So here in precedence diagramming method, it's much easier that every bar is represented by a box in this case. So what we have here, for example, is a box representing the activity, showing the ID of the activity, number 10, the name of the activity mobilized, and the duration of the activity, followed by another successor, or actually 2 successors, number 20 and number 30, begin construction and site fencing, 2 days and 3 days respectively. And here it shows the relationship between the activity. Looking at the box, we're going to find out that the box has basically 2 vertical lines, the left side and the right side. Since we already agreed that the network is always going to flow from left to right, we're going to call this left side the start side of the activity, whereas the right side is going to be the finish side of the activity. Now looking at the line connecting 2 consecutive activities like 10 and 20 or 10 and 30, we're going to find that it starts from the right side of the activity, which is called the finish side, and ends at the left side of its successor, which is called the start side. Therefore, this relationship is going to be called FS, or finish to start, because it starts from the finish side and ends at the start side of the successor. And here we have the number 0, which shows that there's no lag between these two activities, which means activity 20 is going to start as soon as activity 10 is complete. Now, whether we add this 0 or not is basically redundant. So if we had 0, then it means it starts immediately. If we do not add anything, it should be understood as exactly the same thing. So the relationship between 10 and 30 is exactly the same as between 10 and 20. It's still finished to start with 0 lag. We did not have to add that because, again, this should be understood from the flow of the network. If, however, we add any positive number or negative number here, we're going to see what's the significance of these numbers in a couple of slides. The network should start with one node and end with one node, as we have done before. As usual, it flows from left to right. Therefore, the arrowhead is redundant. Activities can only be linked either from the start side or from the finish side, or sometimes from both. We're going to see that in a few minutes. We can never connect the activities from the middle of the box. That would be a big mistake, to connect the activities from anywhere other than the start side or the finish side of the activity. The concept of lags and leads. Lags and leads are pretty much the same thing, by the way. Lags and leads. If you're looking, for example, at two cars in a race car, and one of them is ahead of the other by, let's say, a couple of yards or whatever, in a very fast NASCAR racing, for example. You can say that the car number 1 is leading car number 2 by 2 yards, or you can say that car number 2 is lagging by 2 yards behind car number 1. So basically the lead and the lag are exactly the same thing, depending on, it only varies depending on where are you looking from. If you're looking from the one that's ahead, you say we are leading, or if you're looking from the one that's behind, you say we are lagging. So a lag is a minimum waiting period between a start or an end, finish of an activity, and the start or end of its successor. So for example, a large concrete slab where the rebar can start after the start of formwork, but not necessarily wait for its completion. I have a large concrete slab for a warehouse, for example, a slab on grade, and the activities are going to be basically formwork for the sides of that slab, or even if it's a suspended slab, not necessarily a slab on grade. If it's a suspended slab, then we have the formwork, and then we place the rebar, we place the mechanical, electrical inserts, and then we place the concrete. Now, if it's a large slab, you don't have to wait for the whole formwork to be done to start working on either the rebar or the mechanical, electrical inserts. You can start a little bit after the start of the formwork when you have enough work to do, so you don't have to wait until the formwork is complete. Therefore, in this case, we say that the rebar is going to start after the start of the formwork, not necessarily after the completion of the formwork. It does not have to wait until the completion of the formwork. So in this case, the relationship is going to be a start to start, but there's going to be some lag. You cannot start on the same day. You have to have enough buffer. You have to have enough work done on the formwork in order to be able to start the rebar. So the arrow networks cannot accommodate a lag, and this is the main reason for falling out of favor, especially in the construction industry. A lead is the same as the lag looked at from the opposite side. An overlap, on the other hand, is a negative lag. So think about it for a second. If you say that activity number 2 starts 3 days before the completion of activity number 1, which means there's going to be an overlap of 3 days between the durations of these two activities. So as if we are moving in the opposite direction, therefore it's going to be a negative lag. Lag is usually going to be a positive number. Overlap is going to be a negative number. So when we look at the node diagram drawing, nodes should be drawn as squares or as rectangles, basically. Do not connect the nodes from the top or the bottom. So this is wrong and this is wrong, because again we mentioned that the relationship is going to start either from the start or the finish of the activity. So this is somewhere in the middle, which does not mean anything, especially that the boxes are of the same size and the location of the line does not represent any scale. So connect sides only. The left side represents the start side and the right side represents the end or the finish side. So here, for example, this is improper for several reasons. First of all, it flows from right to left, and it's connecting the middle of the activities. This one is correct because it flows from left to right, and it connects the end of an activity to the start of its immediate successor. When you draw, do not combine relationship lines. So a common line like that branches into two lines, this is not a very proper representation. It can be tolerated, but it's not the best presentation. So we want to show separate lines for the relationships between the activities. So this is the more correct way of drawing the relationships among the activities. To minimize line crossings, when two lines must intersect, make a jump on one of them. So do not do just a simple cross like that, but show that there's a jump through this half circle of one activity over the other. It conveys exactly the same meaning. Some of the advantage of the PDM or the node network: it's easier to draw, does not require dummy activities, as we just mentioned. It's going to be a translation of one-on-one between the Gantt chart and the PDM. Can accommodate lags and overlaps, which could not be shown in arrow diagramming method. Can accommodate constraints, which we're going to discuss in a future lecture. Allows for both contiguous and non-contiguous activity durations. Maybe this is a new word for you. Contiguous. It's different from continuous. Contiguous, it's very close to it in its meaning to continuous, but it means that once you start the activity, you have to keep working until its completion. You cannot start, pause, and resume later and finish the activity. So once started, it has to keep going until its completion. An example of that would be placing concrete in a monolithical fashion. When you say that this slab is monolithical, it means that it does not have any joints, any expansion or construction joints. So once you start it, you'll have to keep placing it. Primarily, it does not have a construction joint. Once you start it, you'll have to keep placing the concrete for that slab until it's complete. One of the advantages also is that it can represent not just finish to start relationships, but as we're going to see in a second, other types as well, including start to start, finish to finish, as well as the very rarely used start to finish. Now today we're going to talk about start to finish. I don't think you're going to be exposed to it in any practical way. I remember over my 20 plus years of experience in the construction industry, I had to use it only maybe once or twice, and basically I would assume that you're not going to have to use it at all, but we're going to learn about it anyway. So here we have an example. Draw the network, the node network, for the following project with these activities. This is very similar to what we had in arrow diagramming, but the difference here is that each letter represents an activity. In arrow diagramming it was IJ, so it could be an activity AB or something like that. But here A is an activity on its own, B is an activity on its own. So when we look at this table here, we find out that A is the starting activity of the network, does not have any immediate predecessors, that's why it depends on nothing. Activities B, C, and D are all immediate successors of activity A because they depend on A. E and F depend on B, and F depends on both B and C, and then G depends on D, E, and F. So I'd like you to try drawing this network on a piece of paper. When we talk about the network calculations, just like ADM, PDM calculations also include a forward path and a backward path, and by the comparison of the forward and the backward, we find what's called the critical path. Same rules, exactly the same rules apply. We start from left to right, we start on day 0, start adding the durations until we reach the end of the network, and that would be our forward path. In case one activity had two immediate predecessors, we take the larger date in the forward path, and that's going to be the start of the successor activity until we reach the end of the network. Once we reach the end of the network, that's going to give us the early dates of that network, early start and early finish. We're going to use the early finish exactly as the same late finish for that network and start moving backwards, which is going to be the backward path. Whatever we did in the forward path, we're going to reverse it in the backward path. Instead of moving from left to right, we're going to start moving from right to left. Instead of adding durations, we're going to subtract duration. Now we're going to have another element, which is the element of lags and overlaps. The lag, as we said, is going to be a positive number, so it's going to be added as we move forward. And the lag, which used to be a positive number added in the forward pass, is going to be subtracted in the backward pass. On the other hand, the overlap, which we mentioned, is going to be a negative number, so the overlap is going to be subtracted in the forward pass, and when we reverse, going in the backward pass, we're going to add the overlaps. Again, don't worry about that. We're going to see a numerical example on network calculations, which is going to illustrate this issue, and it's going to be extremely straightforward. So the early start of an activity is equal to the maximum of the early finishes of all of its predecessors plus any lag or overlap that's going to be factored in, and the early finish of an activity is equal to its early start plus its duration. In the backward pass, running from right to left, it's used to determine the late finish and the late start of each activity. Late finish of the activity is equal to the minimum of the early finishes of all of its predecessors minus lag or overlap. Late start of the activity is equal to late finish minus duration. Again, exactly the same rules that we used for arrow diagramming method. Now again, we're going to be faced with the issues of floats. As we learned last time, we had total float and free float, and we talked about something called interfering float, which we're not going to use. So here we're going to focus primarily on total float and free float. The definition is exactly the same. The total float is the amount of time by which a non-critical activity can be delayed without delaying the whole project. Whereas the free float, we're going to change the last couple of words, it's the amount of time by which a non-critical activity can be delayed without delaying its immediate successor. We're not looking to the end of the project, we're just looking for the immediate successor. And as we agreed last time also, the free float is a subset of the total float, which means the free float can never exceed the total float. Remember that quite well, because this is one of the common mistakes that I usually see on assignments and on exams. Someone giving a total float of 3 and a free float of 5, that can never happen. The maximum of the free float can be equal to the total float of the activity. The minimum for the free float, it can be equal to 0. The free float can never be a negative value. Again, remember that, because this is another common mistake. So the free float has boundaries. The lowest one is 0. The highest one is equal to the total float of the activity. Activities whose total float is 0 are on the critical path. And if an activity is on the critical path, by default, its total float is 0. And if the total float is 0, then definitely the free float is also going to be equal to 0, because it cannot exceed the total float and it cannot be a negative value. Therefore, the only value left is 0. To calculate the total float is equal to the late finish minus the early finish, or the late start minus the early start. So again, you calculate it from either side of the activity, late minus early for the same side, late start minus early start, or late finish minus early finish. Now for the free float, it's a little bit more complex when it comes to PDM, because we may have different types of relationships. We may have lags and overlaps and so on and so forth. So I invented a method to calculate the free float, and it's called the SAT method to calculate the free float. And if you follow it, you're going to find that it's the simplest and easiest way to calculate the free float of an activity. The free float of an activity is equal to the total float of that activity minus the largest total float of any of its immediate successors. Listen again. It's equal to the total float of the activity minus the largest of the total floats of any of its immediate successors. So if we have an activity having a total float of 5, and its immediate successors have total floats of 5, 3, and 6. So in this case, according to the Saad method, the free float of this activity is equal to 5 minus the largest total float of 5, 3, and 6, which is 6. 5 minus 6 is negative 1. But we just said that the free float cannot be negative. In case you get a negative value, put the free float equal to 0. So another example, if an activity has two immediate successors, the first activity has 5 days of total float, its immediate successors have floats of 3 and 2, then the free float of this activity is equal to 5 minus the larger of the 3 and 2, which is 3, so 5 minus 3, that gives 2 days of free float for that activity. There's a general understanding on how to draw the activities in a network, and it's something like this box here, where we divide it primarily into 7 components, 7 compartments. In the middle here, we're going to have the activity ID or its description. What is that activity about? And in the middle at the bottom, we're going to have the duration, which is going to be given or calculated primarily. And then based on that, we're going to perform our calculations. We're going to calculate the early start plus duration gives the early finish. The late finish minus duration gives the late start. Late start minus early start, or late finish minus early finish, is going to give the total float. So the only number that we start with is the duration, and based on the duration, which we acquire from Q over P. Remember that very simple equation that we said is always going to be with us. Q divided by P, Q the amount of work to be done, divided by P the lowest production rate of any of the resources involved in that activity. So Q over P gives the duration, and from that we can calculate all the other dates for that activity depending on the relationship linking this activity to other activities. Precedence networks, some people would like to make a distinction between AON and precedence. I do not usually make the distinction. I consider them the same thing. So precedence network have these 4 types of relationships: finish to start, start to start, finish to finish, and start to finish. So besides relationship types, each relationship can be accompanied by a lag or overlap value. So if it's a finish to start with lag, meaning that the successor is going to start 3 days after the completion of the predecessor. Examples for that: we have placed the concrete for a slab, and the next activity is to remove the formwork for that slab. Of course, we cannot remove the formwork as soon as we have finished placing the concrete. We have to wait for this concrete to have setting, initial setting, and part of the permanent setting, dependent on the code, depending on the span, depending on the concrete mix, depending on the weather and other conditions, and so on. So we have to wait, for example, let's say a week after the concrete has gained enough strength before being able to remove the formwork. So in this case, we're going to say that removal of formwork is going to lag 7 days after the completion of placing that concrete slab. The lag values indicate the amount of delay between the 2 elements of the relationship described by the relationship type. So if it's a start to start, the start of the successor is going to lag by a certain number of days after the start of the predecessor. If it's a finish to finish, the completion of the second activity is going to lag a certain number of days after the completion of the first one, and so on and so forth. 2 ways to present different relationships. So if we have just an arrow spanning between the end of an activity and the start of the other one, it would be a finish to start. However, if we want to designate a start to start, we can draw it from the start of the activity to the start of the successor, or use the traditional finish to start designation and put on it the 2 letters representing the connecting ends of the activity, SS for start to start, or FF for finish to finish. Honestly, I do not prefer this. However, you might see it in some books or articles or publications. I do not use this one, so forget about this one. We're not going to use it. To designate start to start, this is the one that we're going to use, which has less confusion. It shows that the relationship is from the start of the predecessor to the start of the successor, and usually in most cases here we're going to have a positive number which represents a lag. And similarly for finish to finish, it's going to be from the finish of one activity here to the finish of its immediate successor, and so on. Now, since we talked about contiguous activities, which we meant that these are activities that once started cannot stop until the activity is complete, the other option is called interruptible activities, which are activities that can be interrupted, paused for a certain number of days, and then resumed at a later date and completed at the end. So we have two different types of calculations. One of them is going to be based on a contiguous activity assumption, and the other one is going to be based on an interruptible activity assumption. We're going to look at both examples in a numerical example that we're going to solve in another lecture. So the contiguous activities cannot be interrupted, and once started, they must continue until they are finished. For the finish to start relationship in the forward pass, the early finish is equal to the early start plus the duration. And the early start of the successor activity is going to be the maximum of all predecessor dates, which might be the largest early finish of the previous activities, plus any lag or overlap values between the two activities that's going to appear on the arrow or the relationship between the activities. In the backward pass, again, the backward pass determines or provides the late dates, late start and late finish for the activity. It begins at the last activity on the network, moving backwards. So the late finish of the activity is going to be the minimum of all the successors, late start plus lag or overlap, and the late start is going to be the late finish minus the duration, because we move from right to left, subtracting. In case of start to start, again, it's exactly the same concept. We're going to look at the largest number coming to the start of this activity, whether it's coming from the immediate predecessors, whether it has lags or overlaps and so on. We are going to factor that into our calculation. In some cases, we might have something called a dangling activity or open-ended activity. This is not a good thing to have in a network, but it might happen in some projects. To give you an example, something like landscaping activities. If we're talking about a 5-story building, when can we start the landscaping activities? Well, we can start them as soon as the enclosure of the building is complete, so that we do not have any heavy equipment on the outside of the building. We still have a lot of work to be done inside the building, all the interior finishing and so on and so forth, but we can start the landscaping at that point. Now, when does the landscaping need to be finished? It needs to be finished by the end of the project. If the landscape is going to take 2 months and the interior finishing is going to take 5 months, if we start the landscaping once the enclosure is complete, it's going to start and then it's going to be done in 2 months. It still has 3 months of total float until the end of the project, because we are still working on the inside. So in this case, we say that this is an open-ended activity or dangling activity. A dangling activity has either no predecessors or no successors. Should be avoided as they reflect a false amount of float. Again, it would appear in this case that the landscaping has a huge amount of total float, but we can tie it to other activities on the construction site. The dates may vary depending on whether the activity duration is contiguous or interruptible. We're going to see that again in the numerical example. In case of finish to finish, the finish of one activity controls the finish of another, its successor, and it's used to relate to activities that are done in parallel or may have lags. So again, same calculations would apply. Start to finish, as I mentioned before, it's very rarely used, and it's usually linking one non-construction activity like a marketing campaign, for example, to some construction activities. It's used to identify activities whose starts are related to their successors' finish. Difficult to identify a pair of such activities in construction. Again, do not worry about that, because we're not going to have many activities like that in our calculations. As we discussed before, one of the fatal loops in any network, one of the fatal errors in any network is the existence of loops. A loop is activities going back and forth in an unending fashion. So two or more activities linked in a circular manner. You say that activity 2 is a successor to activity 1, and activity 1 is a successor to activity 2, so the calculations keep going in a circle, and that's a fatal error. The software, if we use the software, is going to give you an error that it cannot operate in a loop. It usually can be found in relationships where the arrow turns backward. It's a fatal mistake that should be avoided at all costs and represents a faulty logic. So this is basically an introduction about presence diagramming methods or activity on node. We are going to see in another lecture or another example, we're going to see a numerical example on how to draw them and how to make the calculations and what's the main difference between ADM and PDM. See you in another lecture.